Good morning, students. In our last lecture, we were discussing some numericals for Nernst equation. We saw it as generalized as well as one of its application to calculate the cell potential of the concentration cell. In this lecture, we will do it some few more numericals where we will be applying the Nernst equation to calculate the equilibrium constant for the thermodynamics. Right? Okay. First numerical that we will see it, that is given to us. Calculate the equilibrium constant for a reaction Ni plus Cu plus 2 getting converted into Ni plus 2 plus Cu. E naught of Ni plus 2 Ni, that is given to us as for Ni plus 2 Ni it's given to us minus 0.25 volt, and E naught of Cu plus 2 Cu, that is given to us 0.34 volt. Right? Okay. Now this is the given data to us. Now from the data we know that I want to calculate the equilibrium constant K. Now this reaction, the reaction shows me Cu plus 2 Ni plus 2 Cu. This is 0 plus 2. So it's going it for oxidation, it's going for reduction. That means this one is going to act as anode. Ni gets converted into Ni plus 2 plus 2E. This one will become as cathode. Cu plus 2 plus 2E gets converted into Cu. So that means which reaction is going to act as anode, which one is going to be act as a cathode, that we got it. And on the basis of it, now it becomes an easier to calculate E naught cell. E of left minus E of right. So this we will be getting it as 0.34 minus 0.25. So 0.34 plus 0.25, that is 0.59 volt. So we got it as E naught as 0.59 volt. Now we want to calculate the equilibrium constant. In equilibrium condition, E cell 0.0 volt. In the last lecture we saw it that E naught cell will become 0.0 if it is a concentration cell. When it is in an equilibrium, E cell will become as 0.0 volt. So now what will happen? We will be getting an equation. E naught cell is equals to 0.059 by n log K. This we calculated it 0.059 by n. Electron transfer during the reaction, it's a 2 log K. Therefore log K, that is equals to 0.59 into 2 upon 0.059. Right? Now see, the calculation is much easier. We will be getting it as log K is equals to, this one will become as 10. Right? So 10 into 2, that is 20. So K is equals to NT log of 20. That means we will be getting it as 1 into 10 raised to 20. Now this was an easier calculation. Without calculator we can do it. So I made a calculation. In the routine case, what we are doing it is, wherever required calculator is required, you will make the calculation by using that calculators. Right? So this is a much easier. Once every time I am saying it in the numerical sections, that once if you are able to find out what are the data given to us and what you want to calculate it. Simply by knowing the equation, put the values in it and we'll get the calculation. Right? Now let's see it, something related to even the free energy. Another application of this nernst equation is to calculate the free energy also. We saw the equations, delta G is equals to minus NFE, or delta G is equals to 2.303 RT log K. So using that equations, let's do some numericals based on it also. Now for that case, the question that is given to us, for a cell Mg plus 2, Ag plus Ag. The concentrations that are given to us, it's given to us as an aqueous solutions. Concentrations are not specified in the question. Right? Calculate the equilibrium constant. Calculate the equilibrium constant at 25 degrees Celsius. And also calculate the free energy, maximum work done. Now, for it, it's given to us E naught of mg and E naught of Ag plus Ag. Okay, now from the given data, we know it that this is anode. This is going to act as cathode. So anode reaction will get it as Mg gets converted into Mg plus 2 plus 2E. On the cathode, we will get it as Ag plus plus electron gets converted into Ag. To balance the reaction, we will have to multiply it by 2. So reaction we will be getting it as 2Ag plus plus 2E gets converted into Ag. Right? And net reaction will get it as Mg 2Ag plus Mg plus 2 plus Ag. This is the must required condition. We should write it always, the reactions that are required. Right? Now, E naught cell. We can calculate the E naught as E of left minus E of right, that is 0.80 minus minus 2.37. So we will be getting it as 3.17. We will get it as E naught cell is equals to 3.17. Right? Okay. Once we get it, we can calculate the equilibrium constant. E naught cell is equals to 0.059 by n log k. This value is 3.17. That is equals to 0.059. Electron transfer to log k. So log k, we'll get it as 3.17 into 2 upon 0.059. We got it, suppose answer A. If we get it as an answer A, what we'll do it is k is equals to nt log of E. That will be your first answer, equilibrium constant. Okay. Second factor that is asked to us, maximum work done. So delta G is equals to minus W max, and that is equals to minus NF E cell. This is maximum work done. So delta G naught is equals to minus W max, and that is minus NF E cell. So W max, that will be equals to NF E naught cell. Electron transfer 2, 96500 is Faraday's constant, and cell potential we got it as 3.17. So whatever we got it, that will be the maximum work done, right? So that will be your answer B. Is it? So either by this and then this, or you can do it like this, and then on basis of it, by using minus 2.303 RT log K, also you can calculate the equilibrium constant, right? Let's do it one another sum, similar type of sum. We will just go through it. Now for this, it's given to us, this time it's given to us Al plus 3, the cell potential, it's given to us 0.01 molar salt bridge using Fe plus 2, 0.02 molar Fe. The cell is used. You have been asked, calculate delta G, delta E cell and K. Calculate delta G, E cell and K. E naught of Al plus 3 Al, that is given to us as minus 1.66. E naught of Fe plus 2 Fe, it's given to us as minus 0.44. Now again, this is very useful to us. This one is going to be cathode, this one is going to be anode. So the reaction, we are going to get it as, on anode, we are going to get it as Al changes to Al plus 3 electrons. On cathode, we get it as Fe plus 2E gets converted into Fe, right? Now this is anode and cathode known to us, so can we calculate it as E naught cell, that is equals to E of left minus E of right. We will be getting it as E of left as minus 0.44 minus 1.66, so we will be getting it as minus 0.44 plus 1.66, that is 1.22 volt. We got it as E naught cell, right? Now once we get it E naught cell, can I calculate E cell? E cell is equals to E naught cell minus 0.059 by n log n naught, that is Al plus 3 x Fe plus 2 y, right? Now here, what is the main factor that we needed is, what are n? N is equals to what? We are going to get it 6. The reason is, this whole equation is going to be multiplied by 2, this whole equation is going to be multiplied by 3. So that means we will get it as 2Al gets converted into 2Al plus 6 electrons. 3 Fe plus 2, 6 electrons, 3. So we will be getting it N equals to 6. At the same time, X value, it's going to be 2, Y value, it's going to be 3. So substituting the value, E cell is equals to 1.22 minus 0.059 by 6 log 0.01 raised to 2, 0.02 raised to 3. Make the calculation, simplify it, and you will get the answer. This you can write it as 0.059 by 6 log 1 into 10 raised to minus 4 upon 8 into 10 raised to minus 6. Now simplify it, you will get it as E cell. Make the simplification by using the calculators. First of all, find out the log of it, multiply with this, and then subtract the value from it. So you will get the value of E cell. Okay. Now what is the care that I have to take it for this sum? On the second step. The second step which I want to do it, that is, it's told to me calculate the delta G as well as K. Now while I want to calculate the delta G as well as K, it's not given to me calculated for the standard condition. It's not specified for me. Here, not is not been specified. It's a non-standard. So, in that case, whatever the cell potential we are getting it in a non-standard condition, that we will have to apply it. We can't use it directly 1.22 volt. This is for the standard. So, in that case, what will happen? We will be calculating it as delta G is equals to minus NF E cell. Not is not there being specified. So we will be getting it as 696500 into whatever the calculated answer, the answer that we are getting it, that will be placed over here. That will give me delta G. And using this value of delta G, we will calculate K. Delta G is equals to minus 2.303 RT log K minus 2.303. The value of G we are going to get it over here. It's going to be minus sign with it. R 8.314, T 298 Kelvin, log K. So we will get it as log K, that is equals to minus B upon minus 2.303, 8.314, 298. Minus sign will be cancelled out. So we will get the answer B upon 2.303, 8.314, 298. That is, let us consider it as C. This is log K. But still what we want to do it is K is equals to NT log of your answer C. That is your final answer. Okay. These are the different types of numericals that we did it. There are hundreds of such numericals, right? So make it a practice by yourself. From the textbook, we are having some solved, unsolved, or even the exercise consists of some numericals based on it, right? For the examination point of view, you can say that there will be at least one numerical based on the Nernst equation. Right, so it's going to be very, very important for us. Okay, make a practice by yourself, and this one will be ending our first part of your chapter 3rd. We know it that we divided into 4 parts: electrochemical cell, electrolysis, conductance, resistance, and the cell batteries or corrosion. Right, electrochemical cell, here we are going to end it. That's all for the electrochemical cell. In our next lectures, we will study about the conductance and resistance in the solutions. Thank you.